I mean, the real world, it's hard. It's not like, running experiments on a data set. There was always another guy with the hand on top of a big red button to stop everything in the case that there was a bug and, the robot went crazy.
Hi everyone, Charles here for LLM Papers, and today I am with a huge rock star in the field of machine learning, and especially when it comes to theory, somebody who has extensively studied online learning and related problems. I said a rock star, or maybe should I say, mamma mia. We are here with Francesco Orabona. Francesco, thank you so much for joining us today on this channel. For those who are maybe newer to the field of machine learning and may not necessarily know you, can you please introduce yourself and your background?
Hi everybody, I'm Francesco Orabona. I'm not a rock star by any means. I am an associate professor at KAUST and I do machine learning. A little bit of theory, a little bit of practice. I like to say actually that I am right in between these two topics.
Where did you start before? Did you have a passion more for math or for applications before you started research?
I always had a passion for math. I am one of these students that participated to math Olympiads. But I also did more applied stuff. I also participated to Lego, the Lego bricks.
Oh yes.
Olympiads. This is one of the things that I am most proud of. I am the last Lego world champion.
Really?
And I am the last one because, after the year that I participated, Lego decided to stop this competition, unfortunately. So yeah, I always liked math and I always wanted to do something that was, related to math. And also I have this passion for artificial intelligence that, by the way, many years ago was not what we see now. I mean, it never worked, actually. For many years, AI was not a thing. It was just, a dream. I did my PhD in Genova, in Italy, and I actually did it in robotics. It was not theoretical at all. It was very applied.
Oh.
I spent most of my PhD coding and debugging hardware problems.
Okay.
And the reason for it was that, at that time, the lab in which I did my PhD was sort of the most famous one in Italy for research on something that was, as close as possible to artificial intelligence.
You're doing things which are theoretical, practical, very solid theory stuff. So what took you from robotics to what you're doing nowadays?
Robotics was painful. And I have a lot of respect for people that actually do real robotics because it's really difficult. I mean, the real world, it's hard. It's not like, running experiments on a data set. For example, I remember that every time we were using our robot and gathering data meant that, the robot had to grasp an object on the table and then manipulate it and to take images of the manipulation. Now, when you have a bug in such a system, this means that the robot might smash the table with his arm. And you might damage the table, the robot, and the people around. And so there was somebody looking at all the monitors to see that everything was going correctly. And there was always another guy with the hand on top of a big red button to stop everything in the case that there was a bug and the robot went crazy.
Oh, wow.
So it was really hard. After my PhD, I decided I don't want to see a robot ever again in my life. And so I did a postdoc in Switzerland and I started doing computer vision. Towards the end of my period there, I started studying machine learning papers. My PhD was really hard. I didn't do very well in my PhD. I mean, this is public information. You can just look at my CV. You will see that I didn't publish much. And my postdoc was my real PhD. My supervisor was amazing, Barbara Caputo, by the way. She said, I trust you. I think you will do great things on anything that you work on. Just do whatever you want. Just start studying whatever you want. We can meet twice a day. I can teach everything that I know about machine learning and computer vision. And then, we can work on anything. And so this is what I did. I started studying on my own. I never had a proper course on machine learning, for example, ever in my life. I started studying the papers of online learning for a random chance, by the way, And I discovered the papers by Shai Shalev-Schwartz. Now, Shai Shalev is an amazing researcher because he writes extremely good and clear paper with very strong theory. It's very easy to write strong theory that it's unreadable, but it's difficult to write strong theory that it's very, very clean. I read a lot of his papers, and I read his entire PhD thesis. And I even found bugs in his PhD thesis. If you find his PhD thesis and you look at the acknowledgement, you will find an acknowledgement to me for all the bugs that I found in his PhD thesis.
Oh, that's interesting.
And this is how I learned online learning. I learned online learning through the PhD thesis of Shai Shalev.
I see.
And I fell in love with it, basically. I fell in love with the fact that I could create very strong theory with relatively easy math, because at the end of the day, online learning is very, very easy. This is the secret.
I noticed in online learning that sometimes if we check the proofs, which I encourage to do, is like you have some little tricks or some little things which
Right.
make everything, and it's not really like we need to go into like extremely hard math, but it's like very smart and elegant math which make it like relatively compact
Right.
in the proofs that we can see.
Right. You used the right word. I think you just say tricks. This is a general thing. If you want to do theory, the most important thing is that you have to remember a bunch of tricks. Tricks change from field to field, but it's always about tricks, or I'd say techniques, if you want. From time to time, you encounter something new, and then you have to create a new technique or to, study a new technique. But most of the time, there are few things that you know, and you just try to apply them.
All right, so to get to know you a little more, I'm going to ask you a couple of questions, very quick. You have 50 seconds. Francesco, are you ready?
Yep.
Let's get started. Is it possible to understand machine learning without online learning?
Yes.
What fraction of machine learning could be explained by online learning? 0, 1/4, 2/4, 3/4, or everything?
Half of it.
Should any machine learning research paper contain a proof or at least a theoretical explanation?
No.
Which one is better, New York-style pizza or Chicago-style deep dish pizza?
They are both terrible.
Is a conference paper with an award necessarily a good paper?
No.
Is your best paper and your most cited paper the same?
No.
Has one of your papers ever been rejected from a conference or a journal?
Oh, yeah.
And finally, what is the best YouTube channel to learn about machine learning?
Well, of course, ML new papers.
Thank you so much. Could you please explain at least at a high level and then maybe to more details, what is online learning?
Online learning, it's a sort of a weird machine learning framework. So in standard machine learning, they gather a training set and you train your classifier, your regressor, your predictor, your large language model, whatever, on your training set. And then you will try it on the test set, or you try it in the real world. Now, why this thing works? This thing works because the training data and the test data are coming from the same distribution. Basically, they are related in some way. In online learning, we remove this assumption. In online learning, we say there is an environment. You are interacting with the environment. Every time you take an action, you receive feedback from the action. And based on the feedback, you can update your internal knowledge. But things might change. There is no guarantee that what you learn today will be useful tomorrow. So if you want online learning, it's the easy version of reinforcement learning for people that know what is reinforcement learning. Easy in the sense that, it's a setting in which we can still prove theoretically that certain things will work and certain things will not work. And why it is useful? Because there are certain problems that are intrinsically online. Think about, for example, the classic example, it's stock market prediction. You basically want to invest your money in the stock market, you want to make as much money as possible. And of course, there are a lot of economic steers on how you should do it, but there is also the online learning view on it. The online learning view says anything can happen. It's not true that the past will be predictive of the future. So how can you learn in such a situation? Basically, you give up on the fact that the past will predict the future, and instead you try to do a different thing. Suppose that I knew from the beginning past, present, and future. You know everything. And suppose that you could train one single classifier on all this entire sequence of events. And you want to be as good as that. So this is not a big task. This is not a difficult goal, because again, you are not trying to predict the future. You're just trying to say, I want to be as good as the fixed predictor that was trained with knowledge of the future. And this is possible. In online learning, we proved that it's possible to design algorithms that they only know the past, they have the current input of the present, and they just have to act. And we can show that on average, the performance of these algorithms as will be close to the one of the fixed algorithm that knows everything. Seems impossible, but it's possible.
Then there's one thing which is really interesting that you have been working on recently and that you've pointed out in some of your presentations. Online learning can be connected to other fields and help to derive pack bias bounds that we just mentioned, also concentration inequalities, and so on. Could you say more about that?
This is a little bit more technical, but the idea is that in online learning, there is no assumption on how the world is reacting. The world can react in any way. So basically, we are not making any distributional assumption on the world. And in fact, we prove everything, even in the case in which the world is acting against the algorithm. In other fields, for example, in pack bias, you instead assume that there is a distribution, that it's governing the world. It turns out that this assumption is not really needed, or maybe a little bit more correct. It's needed only at the end of your proof. So you can start from the beginning and you can say, I don't assume anything. The world is completely arbitrary. And let me try to see what's happening. And you can arrive almost at the end. And then in the very last step, you say, oh, by the way, there was a distribution. Things are easy. I can take expectations. And this is the way in which I do my connections. I do everything in the online learning case. I arrive till the end, and then I say, okay, let me use Markov inequality. Let me use Will inequality. Things that depends on the fact that the world is stochastic. And the proof becomes particularly easy in this way because I can take all the results from online learning as they are. I don't have to change them. And then I just have to add one line. And that one line gives me the final result.
I've read a couple of Francesco's paper, and it's not so difficult to read, but to produce that quality of work is actually where the difficulty is, I think. You connected this online learning to like many different fields. Do you think it's possible to connect it to more fields within machine learning?
Oh, I think so. I think every time there is a distributional assumption, you can probably remove it and do an online learning analysis. I mean, you mentioned my work that I did with pack bias, with concentration inequalities. I want to mention also the very recent one that we did in which we link online learning to non-convex, non-smooth optimization. These are two completely different fields, but again, they are connected by the fact that, online learning, it's not about losses, it's not about convex losses, it's about inequalities on arbitrary sequence of data. That's it.
You have done a lot of amazing works. What is the paper or are the papers that you are the most proud of, or what results are you the most proud of?
I think my best two papers, let me mention two.
Sure, of course.
They're related anyway. 10 years ago, I did this paper in which I showed that it's possible to have the same performance of an SVM with kernels with a tuned regularizer on top of a validation set. You could obtain exactly the same performance of this procedure just doing a special kind of SGD without regularization and without learning rates. And the performance was the same from both a theoretical point of view, but also from an empirical point of view. It's the work that I'm most proud of. Also because I did everything by myself. I am the single author of that paper. And it was quite a breakthrough. I remember that one top university in US contacted me, asking me to join basically their university. I said no. And I said no because at that time I was at Yahoo Research in New York, and I actually liked it a lot, and I didn't want to change. A few years after I joined, Yahoo Research collapsed, so I don't know if that was the right choice or not.
And so you mentioned another work, a second paper?
Right. The other one is the one in which 2 years after that, while I was at Yahoo Research, I started collaborating with David Pal. With David, we realized that this stuff that I did in this paper could be recasted as an online betting procedure. And so that is the paper in which we established the connection between betting algorithms and parameter-free algorithms, and if you want, SVM without regularization. Everything was connected, and that is a beautiful paper. The connection, it's the important thing. I believe that connections are more important than results. Every time you link two completely different fields, now what happens is that you can take all the results from these fields and translate to this new field. And you obtain completely new results from a completely different point of view. And this is beautiful.
In machine learning, we have a lot of papers which, no disrespect, I think that's great, but which introduce every time a new algorithm with new guarantees. And sometimes we really need more papers which make like new analysis of existing algorithms or connect different fields. And maybe we don't need so many algorithms, but we need like more connections and more analysis.
Yeah, I agree. Yeah. I like to view things from different point of views.
You briefly mentioned it, but as a connection, because you had like a huge impact in optimization when it comes to online parameter-free learning.
Right. Both these papers are based on the fact that basically you can do stochastic gradient descent without learning grades because you don't need them. This is the truth. It's not that you should tune them or adapt them or learn them. You should not have them. This is the reality. And this is, I think, the biggest contribution of my work, showing the fact that the learning grade should not be there. It's a bug.
In many applications or big system that we have nowadays in AI, we have like a ton of hyperparameters.
Right.
And we have to tune them.
Right.
By ton, I mean like for small things, we're thousands, but if we're talking like ChatGPT, we're talking of millions, I guess. And we have to tune them.
My dream was to create these sort of master algorithms that could optimize anything without knowledge of anything. And it could always obtain the best performance. Nowadays, I think that it's not completely possible. There are situations in which this is true. So as I mentioned, in stochastic gradient descent, Lipschitz losses, convex learning rates are not needed. But in other cases, it's still unclear. So, I'm not completely convinced now that it's possible to remove all the hyperparameters, but at least we can try. We can try to push this idea as much as possible. And you mentioned the LLM. This is actually a very important topic because how do people actually train LLM in these days? An LLM, the actual big ones, will take a couple of months on hundreds of GPUs. So this means that you cannot do cross-validation. You cannot tune the learning rate. You have one chance, and you have to get it right. So practically what people do is that they train very, very small models, a lot of them. They try all the possibilities, they try all the learning rates, and then they try to infer what is the optimal one from the small model to the big ones. And there are also theories that tell you how to do this transfer in the optimal way. But it's still a theoretical thing. It's not really that people actually know what is the best strategy on the big model. Because again, it's too big. You cannot tune it. And so, having a parameter-free procedure for the big model, it is really an important problem. It's not just theory, it's a very practical one.
Guess my algorithm.
We take a little break in our interview to play a little game. We do that sometimes. I will give some names of algorithms, or at least rephrase them. And Francesco, you're going to try to find the actual name of the algorithm, what they correspond to.
Okay.
So there's a lot of puns in the story, probably very bad, all due to me. Are you ready?
Yep.
The first one is, cool down, boss, and I will follow you.
Follow the leader?
Almost. Follow the regularized leader. The next one is, are you guys friends? Can I join you?
Is this clustering, some kind of clustering algorithm?
Yes, absolutely, that's k-means. The next one, I know you can do better than that.
This one I really don't know.
Is the bandit algorithm UCB, upper confidence bound. Next I have, sometimes he makes weird decisions, but that works.
Follow the perturbed leader?
Yes, you got this one right. And the last one is, follow the cool breeze and you will reach a cool spot.
Gradient descent?
Yes. That's it. So there was a topic I would like to mention, but very briefly, because the interview is already quite long. But no, it's very interesting because Francesco Orabona has like many stories to share with us. So I think we're very lucky to have him. So your current research, you're doing also like a lot of theory work and also some practice work. But I'd say that for many of us, theoretical work may be very intimidating. So would you give a roadmap to get started in theoretical work for our viewers who might be interested to do like theory work?
Sure. So as I said, I did a PhD in robotics, and so if I went from coding in C++ and debugging network errors to proving regret guarantees and pack-based bounds, it means that anyone can. Okay, so this is the starting point. I suggest that you actually take a book and you read it from the beginning to the end on a particular topic that you would like to master. You cannot start from the middle. You need a solid background, and you need the book that starts from the very beginning and explains you first the basis, and then you arrive at the very advanced topics. Let me add one thing on how I do research, how I approach research. I start studying something, and then I rewrite everything. I rewrite everything in my notation. So the first thing that I do, I read, for example, a learning paper. I say, why these people called the output of the algorithm W? Typically, they call it W because they wanted to get weights. By the way, this is the historical reason. I don't like it. The output is what you're looking for. It's X. I rewrite everything with X. Why the competitor is not explicitly written? Why there is an infimum over the competitor? This might be undefined. So let me rewrite everything with respect to the competitor. So I rewrite everything. And this is, by the way, my online learning notes, they started from. I was unsatisfied with how people were presenting this stuff. And I started rewriting everything. And the moment that you rewrite everything, you start also understanding the big picture. You start seeing the gaps. You say, oh, wait a moment, I have this topic, I have this topic. There is something in the middle here that is missing, and nobody did it. Maybe I can do it. Many of my papers, they started as just, notes that I have on my hard disk. And at a certain moment, I said, oh, you know what, I can take this, I can transform it into full-fledged paper.
And finally, what are the great upsides of theory, and why should we do theory?
Let me here quote Manfred Warmuth, the godfather of online learning. We also have godfathers, not only the deep learning people. Manfred Warmuth once said, shouting, by the way, he shouted, theory is just a hint, nothing else than a hint. So it's not that we should not do theory for the sake of theory. We should do theory because we care about a problem that we want to solve. And theory tells us, among all the possible things that you could try, this is something that makes sense. It's a hint of what makes sense. And so you start from that, but then you still have to arrive to the real problem. You cannot stop just at the theorem. You have to arrive till the real problem.
Theory is here to guide the experiments and know what we should do to apply it. Thank you so much, Francesco Orabona. Thank you so much for joining us. And thank you for watching this YouTube channel and making what it is. If you enjoyed this video, don't forget to give it a thumbs up, subscribe, hit the bell icon to get notified of my next video. I'll upload new content every week or every 2 weeks, it depends. But anyway, thank you so much for watching. I wish you a wonderful week, and I'll see you in the next video. Cheers.